home how they work. So everyone can learn from experience what's good and what's bad, because the positive and negative outcomes influence your future actions. So, for example, I came to LA a few days early with dreams of becoming an actor, going to movie studios and getting my name on the Hollywood Walk of Fame. But then I got rejection after rejection after rejection. Learning from experience, from feedback, is effective. I know I shouldn't be an actor now, but it can also be a waste of time. Similarly, we can learn from instruction. Had someone told me I was going to fail, I could have saved my first few days here. Through rules, advice, and explicit instructions, we're able to benefit from the knowledge of others. So, the locals of LA can suggest what we conference goers do with our free time. We go to Disneyland, we can look at a map on how to get there, and we can even use an app that helps us avoid the infamous LA traffic. Children and adolescents similarly learn both through experience and instruction. Children have no problems learning that playing with balloons and running around a playground is fun, but we rely on instruction to protect them from potential dangers that we don't want them to experience. So we might say, you can only cross the road when you're holding my hand. As they grow a little bit older, you can cross the road at the crosswalk, but only when the light is green. For adolescents, driving their first car can be a powerfully rewarding experience, but it comes with new dangers. You might temper their enthusiasm by getting them a safer car, a little less flashy, but mostly you rely on years of instruction and rules to get them to drive safely. An assumption inherent in providing such guidance is that instruction can direct behavior as efficiently, if not more, than their own experience. Recent work in adults has looked at how instruction influences your feedback-based learning. So the basic model of feedback-based experiential learning is you take an action, you get an outcome, and that outcome influences whether you'll repeat a similar action in the future, with positive outcomes increasing the likelihood, negative outcomes decreasing the likelihood of repeating that action. And work in adults has shown that when someone communicates through instruction that an action will lead to a specific outcome, that influences that feedback-based signal. So if I tell you, this is a good action, something good's going to come from it, you take that action and you get a good outcome, the feedback-based signal is amplified. Whereas, even though I say it's good, but you got a bad outcome, that feedback signal is diminished. This is similar to the confirmation bias, where you value experience more that fits with what you've already been told. So, a critical part of the feedback-based learning signal is a reward prediction error, which is a dopaminergic input on the ventral striatum. And theoretical models and imaging studies in adults has shown that the instruction influences that signal through prefrontal input on the ventral striatum. This the feedback learning signal seems intact in children and adolescents, if not overactive in adolescence, whereas there's a general maturation of the corticostriatal circuitry, which suggests that there may be a limited effect or limited influence of instruction on this feedback-based signal in children and adolescents. So how do we look at that? How do we look at whether instruction is influencing experiential learning similarly across development? So take, for example, consider two actions that have been equally reinforced, but one of them has had instruction about it. We're expecting that adults will show an instruction bias, so they'll prefer an action that has been instructed, and here we're hypothesizing that children and adolescents will not show that instruction bias and rely more on their experience. So to test that, we used a task where both types of learning occur at the same time and modified it for children. So children and adolescents, all individuals are told they need to feed this mouse by finding cheese in a mouse hole. And for each pair of mouse holes, they're told one is going to have cheese in it more often than the other, and it's their job to collect as much cheese as possible from each of these 3 pairs. It's difficult, so we give them a hint that the yellow mouse hole has cheese in it most of the time. So the task design consists of 180 trials during the learning phase, where in addition to that instruction, they learn from experience which mouse hole is more likely to have cheese than the other, followed by a test phase in which we can assess whether it's the instruction or the experience that's driving their decisions. We have similar sample sizes in each group. Children were 6 to 12, adolescents 13 to 17, and adults were 18 and over. So I'm going to run through a few trials so you can get a sense for the task. Just yell out the color you think has cheese behind it. And remember, yellow's the good one. Blue or orange?
Orange.
I heard orange. Orange is good. Green or yellow?
Yellow.
Yellow. Wrong. Orange or blue? I heard blue. Blue is good. Yellow or green?
Yellow.
Yellow. Wrong again. Green or yellow?
Green.
Green. Correct. All right. So these were the actual reward contingencies for each of the pairs. And for every 10 trials they saw, these were the actual outcomes that came out. And what you might have noticed is the yellow one was actually not good. We gave them false information. And by putting instruction in direct competition with experience, we're better able to assess during the test phase which one is driving their decisions. So the test phase consists of the 3 initial pairings and then all possible combinations of pairs. There's no feedback given during the test phase, so they're doing no additional learning. It's just an assessment of what they have learned so far. And we can get a sense of whether they learn simply which one was good or bad within a pair, or if they can tell the difference between the stimulus that was rewarded 80% of the time and one that was rewarded 70% of the time. And more importantly, when we consider 2 pairs that have stimuli that were rewarded exactly the same amount of time, but were instructed differently, that's where we can see where instruction is leading them to change their behavior. So now we're just going to look at the pattern of behavior during the learning phase, so to look at what they've learned. The x-axis is time through the phase, and broken up into 10 trial blocks, and the y-axis is optimal choice. Optimal choice being choosing the option that has the higher likelihood of being rewarded, not choosing the one that was rewarded. So we expect all age groups to choose above chance by the end of the phase. And what we see for the easy uninstructed pair is that all groups are performing above chance, and for both uninstructed pairs, adults do seem to be performing better than children and adolescents, but they're all performing above chance. Then for the instructed stimulus, all groups initially followed the instruction, as you guys did, and then through the learning phase, they showed evidence of learning that the other stimulus was actually the more optimal one. So this is sort of what they've learned, and it's in the test phase that we can then see how they're using the information they gathered here to make their decisions. Are they following instruction that yellow is good, even though they might have learned otherwise, or are they following their experience where the yellow is bad? So to look at that, let's consider these 2 options. So during the learning phase, they were reinforced exactly the same way. But the yellow was instructed and the red was not. So we expect, again, adults to favor this instructed stimulus and children and adolescents not to. So to look at that, with this pair, we're just looking at the percent of time that they chose the instructed stimulus. Anything above 50% is a bias towards following the instruction, and we see that adults significantly prefer the instructed stimulus, whereas children, and especially adolescents, don't show that bias. Next, I'm going to go through how you can combine different sets of pairs to come up with an instruction bias score. So let's consider the 80-30 pair during the test phase. For the learning phase, these were the reward outcomes that the individuals experienced. And so for the test phase, the performance is how often do you choose the blue stimulus. And then we can compare that to equally experienced but differently instructed pairs. So if you follow the instruction, then you're overvaluing the yellow stimulus, and that drives down your accuracy for this pair. And so by looking at the difference between those pairs, that's the effect of the instruction that you're having. We can do that for other sets of pairs. Here, if you're following the instruction, again, it's increasing your value of that 30, and here improves your accuracy relative to the pair where you only experienced it. By averaging those together, we get an instruction bias score where everything above 0 is a bias that's consistent with the instruction that we gave. And again, we see that adults have this instruction bias, so instruction seems to be influencing their feedback-based learning, whereas in children and adolescents, they show a minimal effect of instruction, suggesting they're relying more on their own experience and not the instruction that they were given. When we look at it continuously by age, we see a positive correlation between instruction bias and age. Okay, so we replicated the finding that in adults, instruction seems to be influencing the feedback-based learning signal. And in children and adolescents, the relative immaturity of the prefrontal cortex and the corticostriatal circuitry might be what's leading to that lack of instruction bias. This fits with a broader literature of gradual development of cognitive control ability, and though that's sometimes the lack of cognitive control is sometimes considered a developmental handicap, a lot of work recently has been looking at how it can be beneficial by allowing implicit learning to occur unhindered, and that might promote pattern recognition, development of language and social conventions, and the development of independence. So an important question at the end, especially for people interested in protecting children and adolescents, is, are they listening? Yes, they are. In our data and from your own experience, you know that they listen initially at least. So here all groups initially followed our instructions and only moved away from that instruction when the experience conflicted with that. So it gets tricky when the experience they have and the instruction they're given might be in conflict with each other. Studies of public policy campaigns have shown that they can be ineffective in deterring risky behavior. And the thinking behind that is that even though they're given instruction that an action might be bad, there are common positive outcomes, social and hedonic outcomes, and rare negative consequences. And that might lead the experience to conflict with the instruction and lead them to use mostly their own experience and not the instruction in developing their risk assessment. So this just drives home the point that this is it's a difficult task to curb risky behavior in adolescents. So to summarize, we found that feedback-based learning in adults is biased by explicit instructions, which was found previously, whereas in children and adolescents it was not. And we suggest that the prolonged corticostriatal maturation may lead children and adolescents to learn more from their own experience than they do from instruction. We're interested in following this up further to see what, if anything, might push the instruction effect in one direction or another. I'd like to thank everyone in my lab for helping run the study, co-authors on the paper, Brad Dahl, the collaborator from NYU, funding sources, and especially Kate Hartley for driving the project and mentoring.